Hello everyone. Today this week we are starting lecture 25 where we are going to discuss about pseudomorphic HEMTs and also indium phosphide HEMTs based on compound semiconductors of the gallium arsenide indium phosphide family. We had discussed in the last week about the traditional gas HEMT or MOSFETs. We discussed their working and different issues and aspects related to them. However, they are not sufficient for many application. We need to improve the performance, especially for millimeter wave and microwave power and low noise application. You need better performance than a baseline gas HEMT. So today we will discuss precisely that. The devices that we are talking about here are also eminently commercially available. They are useful in a lot of application, both civilian and military. We will discuss all of these aspects and also look into the practical things that are related to these devices. Okay. So over to the whiteboard here. So we will talk about pHEMT stands for pseudomorphic HEMT. We will see what pseudomorphic means, and then indium phosphide HEMT. So what are these HEMTs? These are also HEMTs, but they are a little different. So in what way are they different? So the idea is that the traditional HEMT that we had was not good enough for many application, or in other words the question was, can we improve the HEMT and still get a better performance, and can you get better performance? In other words, can we get better HEMT? Okay, can we get better HEMT? So what are the problems with normal HEMT? Normal HEMT problem is that this band offset between gas is not very high. So the 2DEG density that you can get here is also limited. Okay, 10 to the power 12 per centimeter square, for instance. Is it possible to increase this delta EC, this band offset, so that I can get a better 2DEG density? That is one question. Can I get a backside barrier, as we have discussed this also previously, so that I can have a better confinement of the carriers? This gas layer, if you use gas, for instance aluminum gallium arsenide, here it is said indium aluminum arsenide because it is a different HEMT. I am talking about a normal gas HEMT. You can increase the aluminum composition there to increase the barrier and also to increase this delta EC, but with higher levels of aluminum in gas you have more defects called DX centers. These are deep level centers which are not good for the device. Okay. So people had tried to see what material system in this family of material can be employed for making HEMT such that I get a better mobility of electron, maybe I get better velocity of electron, I get more density of higher density of electron gas, I can reduce the parasitic. So this will help me improve the cutoff frequency FT Fmax, maybe this will help me improve the breakdown voltage, maybe this will help me improve the transconductance. So the idea was to have a higher mu times NS product because that gives you the sheet resistance. For that people realize that you need a quantum well like this, which is confined from both sides. You need a material, this is a material, the channel material, you need a material where fundamentally the electron mobility and electron velocity are much higher than that in gallium arsenide, and as I told you, you can get that with indium gallium arsenide, and higher the indium content better is the mobility, velocity, etc., etc. However, indium gallium arsenide does not have the same lattice constant as gallium arsenide because you are going to grow this on gallium arsenide substrate. So gallium arsenide lattice constant and indium gallium arsenide lattice constant is not the same, which means the indium gallium arsenide will have a strain in the layer because you are growing a mismatched layer, and you do not want to grow too much of a strain because it will relax and it will create misfit dislocations. So there is a limit to which you can put indium, and it typically turns out to be around 10 to 15 maybe 20% indium. Beyond that it will significantly strain and relax, you do not want that. So you need to have a low a range of indium possible such that this layer is strained to the layer below, which is gallium arsenide. Okay. And InGas also gives you higher velocity, by the way, apart from higher mobility. Okay. So this is a strain, it is strain, and that is why it is called pseudomorphic. Pseudomorphic means it is strain, it is the layer that you are growing, the InGas layer that you are growing, you are forcing it to mimic the crystal structure of the layer below, and InGas has the strain that is accommodated in it. It is called pseudomorphic HEMT. You are trying to get the benefit of InGas as a channel as opposed to a gas as a channel. Number 1, higher velocity, number 2, higher mobility, number 3, better confinement with a quantum well, number 4, the delta EC could be engineered to higher value so that you have higher 2DEG density. Okay. This is the holy grail of the same thing. Okay. Now how do you do that? This is the funda of strain. So you have the gallium arsenide substrate with a certain lattice constant, okay, and you grow indium gallium arsenide on top of that. So there is a lattice mismatch. You can see InGas has higher lattice constant. This spacing is more than this spacing. correct. So, you are forcing the InGas to grow on top of gallium arsenide by making them forcefully fit to the lattice below. You are also forcing the L-gas to fit the lattice below, but L-gas and gas have similar lattice constant. This is not drawn to scale. So, this layer of InGas, which is the channel layer, okay, this is your InGas channel layer, and it can have a certain thickness and certain composition. I told you the composition of indium cannot be too high, it can be only 10-20%. This is strained, that is why it is called a strained HEMT or a pseudomorphic HEMT. Okay. There is a critical thickness also of this channel, you cannot exceed that, otherwise it will relax. Okay. Of course, you are free to play with different layers here. You can see there is a indium aluminum arsenide layer here. Why? It is very interesting. You can play with different kind of layer, indium gallium phosphide, indium aluminum arsenide, but the core essence or the core crux is this. Okay. So, you are having a strain layer, you are going to strain this layer to get better benefits at the device level. So, how does the structure look like? Your substrate is also always, in this case, gallium arsenide, which is semi insulating, SI, it stands for semi insulating. People drop it with chromium or something to make it insulating or resistive. Then you have a buffer layer. This buffer layer is basically undoped gallium arsenide, it separates the substrate from the active layers. Then you have on the top of the buffer layer, you have the channel. The channel is InGas, which is 15% of indium content, and this channel thickness could be, depends, depends, could be few 10 nanometer or whatever, depends on the critical thickness here, and the 2D electron gas will form in this InGas only, which is why this 2D electron gas is. And on top of that, you have a barrier, which is in this case n-doped aluminum 30% L-gas, aluminum indium arsenide. The reason they use aluminum indium arsenide is because it can give you a delta higher band offset as compared to if you use L-gas InGas on top of, but instead of that, if you use indium aluminum arsenide on top of InGas, then your delta EC will be higher, so you will get better 2D electron gas. And on top of that, of course, you have an N plus gas cap, which helps you improve the contact resistance. This could be uniformly doped or this could be delta doped. Okay. So, typically the lattice mismatch that happens between InGas and the gas below is typically 1 to 2%. Do not want to increase the lattice mismatch too much. And typical thickness of the channel here, the InGas channel, is around 20 nanometer. You can see this is 20 nanometer, but again it depends on the mismatch. You are having the strain layer, and the strain is basically accommodated coherently in the quantum well. That means the quantum well, the well, this is the well, this is going to make the well, correct, this is going to make the well. This well takes the strain, it coherently takes the strain, accommodates it, and there is no dislocation because you do not let the layer relax. If you grow more than critical thickness, if you grow say 40-50 nanometer of InGas 25%, yes, it will relax, it will create dislocations or extended defects. We do not let them happen. You only let it get strained without creating any dislocation, without creating any relaxation. So, that is why it is called a pseudomorphic material. The maximum indium content is, as I told you, 15 to 20%, but people can go to 25% also, but at 25% your thickness of the InGas channel will be reduced, because if you increase the composition, your critical thickness of relaxation also will will reduce. So, beyond the dislocations will appear, you do not want the dislocation. Okay. And the aluminum content in the barrier could be around 25%, no more, because again it will get strained. The aluminum arsenide or indium aluminum arsenide that you are putting on top also is getting strained to the gas below, gallium arsenide layer below. So, you do not want a very high aluminum content, otherwise you will start straining the barrier, and again dislocations will appear there. Okay. So, this is a pseudomorphic HEMT, and it gives you much higher electron velocity, electron mobility, and you can get better 2D electron gas density. So, you have higher cutoff frequency, lower parasitics, higher GM, okay, better FTF max, better GM and channel control, and lower parasitics. All these advantages are there for this kind of HEMT compared to the baseline L-gas HEMT that we discussed last week. So, this helps in making pseudomorphic HEMT extremely good for say low noise application. Not only that, it can also help you improve the power performance, and so it will be useful for power amplifier also. For power amplifier, you use things like double recess, okay, you use like field plates, all these techniques you use, and you can get good power performance also. So, if you look at millimeter wave, so millimeter wave typically means 330 to 300 gigahertz. This is your millimeter wave frequency. If you want millimeter wave power, which means you want a power amplifier to deliver power or amplify power at any of these frequency ranges, then what are the design considerations, what are the critical aspects that you need to care about for a pseudomorphic HEMT. So the first thing to care about is that for a millimeter wave power amplifier where you need higher current density, you need to have higher 2dEg density. To get higher 2dEg density, people do delta doping on both top side and back side of the channel. So if this is your channel, 15 nanometer, 15 nanometer of in-gas where indium content is 22%. If this is your channel, you have a spacer on both sides. You see there is a 3 nanometer spacer on the top, a 3 nanometer spacer on the bottom, and this spacer is L-gas, okay, with aluminum 25%. This L-gas spacer is of course undoped. Then you have a delta dope layer, silicon delta doping 5 into 10 to the power 12. Silicon backside doping could be little lower because otherwise you will have a parasitic channel 1 to 2 into 10 to the power 12. You are using two different dopings, two different layers of delta dope, so that the electrons will be donated from here, the channel has more 2d electron gas density. So this boosts the 2d electron gas density, having delta doping on both top and below. Now you can get 2d electron gas density around 3.5 into 10 to the power 12, which is significantly higher than what you would get in an L-gas HEMT. This is good for high current densities. Your mobility is 5000, not the best of mobilities, but your mobility is still very good. The breakdown voltage of such a device, just like any other HEMT, will be due to either impact ionization in the channel. So the channel is in-gas, so in-gas has a lower band gap material. So the in-gas fundamentally has a lower breakdown voltage because its critical field is lower. So the impact ionization might start in the in-gas channel between the gate and the drain where the field is high, or it could be a surface leakage. You know, you can have you'll do a recess and put down the gate and the drain might have a surface component of leakage that also might come from the gate, that might come from the passivation, the H damage, etc., it can also lead to a breakdown voltage, but typically for millimeter wave power the breakdown is around 8 to 15 volt across different devices of pseudomorphic HEMT architectures. You can use field plate, you can use double recess, you can use this buffer that you are growing, you can grow at low temperature. This is a material science problem, by the way. If you grow low temperature buffer, in this case there is an SL buffer. SL stands for super lattice. There is L-gas, gas, few nanometer L-gas, few nanometer gas, few nanometer L-gas, few nanometer gas. So that is like a super lattice, you grow sufficiently thick. So these are all done to minimize the material imperfections and defects, and low temperature, LT stands for low temperature or super lattice buffer here can help improve the breakdown voltage, okay, or it can help improve the buffer quality because it will lead to a reduced buffer leakage path. We will discuss about this in gallium nitride HEMT also, because there also people talk about low temperature buffer and super lattice buffer, but this is useful for improving the quality of the material, the buffer, so that the leakage is reduced, okay, very important. Now this is a table taken from a book. Of course it has many data points. We just have to take a glimpse and get a feel for what it means. It basically shows you some of the state of the art values, but when I say state of the art, it is still about 10 to 12 years old, but does not change anything. We still continue on the similar trend, or I mean things, the main concepts become very clear when you look at data from such time. You know, everything in the recent, you do not have to look everything most latest, you can look at 10 to 12 years old data also, and you will get sufficiently high insight, good quality insight. So this is gallium arsenide pseudomorphic HEMT for power amplifier. So what are the things that they are showing? Here they are showing the frequency 12 gigahertz, 20 gigahertz, 35, 44, 55, 60, 94 gigahertz. These are different frequency bands. W band, 94 gigahertz is W band, 12 gigahertz is at the border of X band and Q band, okay, Q band, V band, etc. They have different military, strategic, civilian wireless communication applications, drone and other things, okay. These are different frequencies. With higher frequencies your gate length has to come down naturally. So your gate length at 12 gigahertz is suppose 450 nanometer, 0.4 micron, coming, you keep decreasing, you see it is 0.1. 0.1 is basically 100 nanometer gate length. This is your gate length. You have to reduce the gate length for faster devices, because if you want to get power at 94 gigahertz amplify power, then you need to have a cutoff frequency that is maybe 200 to 300 gigahertz. So your gate length has to be lower. If you want to get power at 12 gigahertz, your cutoff frequency could be 30, 40 gigahertz, maybe 50 gigahertz. So gate length does not have to be as small as 0.1 micron. Now this gate width W is a very important parameter. It will determine how much current you get eventually, absolute amps, and that will also determine how much power you get in absolute watt, not just watt per mm, okay. So you can see this device has about 1.05 mm gate width. It is not a single gate line, by the way, you cannot have such a long gate line, okay. You will see that you have to make a multiple finger actually gate and you have to make it HEMT accordingly. This is 1.6 millimeter, this is 0.6 millimeter, 0.4 millimeter, etc. you can see that if you go to higher and higher frequencies, the gate width cannot be much. So, the gate width becomes lower, 40 nanometer microns, 160 micron, 150 micron, 75 micron. Over here you have 1 millimeter, 0.6 millimeter. You see at lower frequency you have the luxury to go to larger gate width devices. We will see that. With higher frequencies you do not have the luxury to go to larger gate width as well as gate length. Okay, gate width is different, gate width is the width of the gate. You cannot even go to larger gate width because there will be propagation delay and phase delays. So, that is why the gate width also comes down at higher frequency. This column gives you power density, that is watt per millimeter, but for the absolute power you have to multiply. So, this device gives you 0.77 watt per millimeter. You have to multiply that by 1.05 millimeter to get the absolute power that you are getting, which is 0.81 watt. Similarly, this is 1.37 millimeter, 1.37 watt per mm, and the periphery is 1.6. So, you are going to get 2.2 watt of power. So, similarly you can see these are all in milliwatts, those were in watts. Okay. When you talk about gallium nitride, you will see that the numbers are one order of magnitude larger, which means the power density for 12 gigahertz device, instead of 0.77 or 1.37 watt per millimeter, people report 10 watt per millimeter, right. So, you can imagine the kind of power you will get in gallium nitride, that is crazy. Anyways, so gain, you can see the gain is 10 dB, 14 dB. Gain is also very sensitive, by the way. You can say the gain is reducing, 2, 3, 4, 6 dB, very little gain. With higher frequency your gain also comes down. PAE is the power added efficiency. We discussed this when we talked about MESFET. It depends on the drain efficiency, which is the output RF power divided by the DC bias into 1 minus 1 by gain. The power added efficiency is very important for battery operated devices like mobile phones, iPads, etc. And you can see the power added efficiency can also vary a lot, but with higher frequency again the power added efficiency comes down only 16-13%. And this column tells you what kind of device architecture you use. HG stands for heterostructure. So, double heterojunction, you have quantum well confined from both sides. LTG, low temperature gallium arsenide buffer. Okay, double heterojunction, double dope channel. Sometimes the channel, instead of in addition to having a 2d electron gas, people also put some mild n-type doping in the channel to improve the 2d electron gas even more at the cost of slightly reduced mobility, because with higher doping, with doping in the channel you are defeating the purpose of modulation doping. So, your mobility will come down, but your channel concentration can be significantly high because there is already a 2dEg, although there is now doping. So, people can get higher current. So, similarly things, double heterojunction. Okay. Here people are talking about the drain bias. This is biased at 7 volt DC on the drain, 5.9 volt. With higher frequencies your biasing also will reduce. You see at this here you have 4 volt, 3.4 volt, 4.3 volt. With lower frequencies you can go to 7 volt, 7.5, 8 volt, 8 volt. Okay. So, this is the drain voltage. You cannot go much higher because the breakdown voltage is around 10 volt. So, that is why you cannot go there. If your breakdown voltage is 15 volt, you can go to around 6-7 volt, that is all. You can see that gallium nitride can go to much higher voltage at this frequencies, and so you can bias it also at higher voltages, and you can get higher current, higher output power, etc., etc. Okay. So, but this is a summary of the gallium arsenide pHEMTs, you can get a feel for that. Now, but this was the absolute powers in milliwatts, all these are in milliwatts. If you want to get in watts, just like this, if you want to get actual power in watts, we call them multi-watt device. If you want to get actual power, amplified power in watt, then you need to have a large gate width. So, if your gate width, instead of the gate width was what was the gate width, 500 micron, 150 micron, 400 micron, instead of that can I use a gate width of 16 millimeter, but this frequency is low, of course, 2.45 gigahertz. Say I take 12 gigahertz or 18 to 12 gigahertz, 21 gigahertz, X band, Q band. Can I have a gate width of 25 millimeter? Can I have a gate width of 8 millimeter? That is seriously high. If I do that, then I can get 10 watts, 11 watts, 12 watts, 6 watts, 4 watts higher power. So, this is called multi-watt device. You can see the gain also is not so high. Power efficiency can be high. You can do at a design level, you can do circuit level tricks to get some good power. You can bias the device at, you can see the bias volts, 7, 8 volt, 9 volt is the maximum that you are biasing the drain at. But this is not very trivial, because you need multiple gate fingers to increase this. And when you have multiple gate fingers, you enable higher current, because the breakdown voltage is going to be same. You are going to use 7 volt or 8 volt, it is fixed, and the power is basically proportional to the voltage they are applying into the current. So, since the voltage is fixed at 7 or 8 volt or 9 volt here, your current has to be high to get higher power. That is why you use multiple finger to get much higher current. how to design and develop such multi-finger HEMT is the key question, because it is not always trivial to design a multi-finger HEMT, because the moment you talk about a multi-finger HEMT, which is this is your source, this is your drain, this is your source, this is a drain, this is a drain. So, this will continue for many fingers, and you have a gate in between, gate. So, you have to connect the gate, you have to connect the drain, you have to connect the source. It is not very trivial, and also the RF signal that comes will have a propagation delay. So, it is not very trivial at all actually. So, what do people do? First thing to understand here is that when you have a large gate width or you have multi-finger gate width, people have to bring in the concept of distributed elements in the gate. You cannot take the gate as just a lumped element of a straight line, you have to consider it as a distributed element, and people model the gate as a distributed network of a gate resistance and incremental over a certain delta, over a certain delta length of the gate, you can say, or a delta width of the gate. There is an incremental gate resistance, there is an incremental gate inductance, which are both in series, and these are in parallel with a gate capacitance. The gate will have a capacitance coupling to the channel. So, that capacitance is in parallel to the wire, the gate metal, not the wire, the metal, which is the inductor. The gate metal also behaves as a resistor, it also behaves as an inductor, because it can store magnetic energy, okay, at any electromagnetic wave when it is coming, it can store magnetic energy. So, a straight line or metallic line or a wire is also an inductor. It does not have to be a wound wire, a wrapping wire, it can be a straight wire, it will still have inductance. So, the inductance and the resistance, and this is the delta Z, this is delta Z. So, you have many elements, you model it, you model the gate something like that. It is a loaded transmission line, this entire thing is a transmission line, by the way. Transmission line is we will come to that when we talk about towards the end of this course about microwave engineering. In RF signal, in electromagnetic signal, you cannot use lumped elements. So, it is a distributed element where you have a line where the electromagnetic signal is propagating, that is your transmission line. You have things like scattering, reflection, etc. However, you can see that because of this incremental inductance, capacitance, resistance, what happens is that as the gate signal is propagating, it is progressively getting attenuated. Attenuated as in its intensity, strength is decreasing, because you have the resistive drop, you have the inductance, you have the capacitance. So, the waveform progressively attenuates as it travels along the gate. So, in this previous thing, as the signal is propagating along the gate, it is attenuating because of these components, and because it is attenuating, the gain GM and even the gain, the large signal gain will drop. That is why with larger gate finger, the gate will drop, correct, your gain will drop. You can see the gain was higher here, of course at higher frequency the gain will always drop. So, the gain is dropping here. So, this is because of the progressive attenuation of the signal as it goes along the gate. Beyond that also there is another problem, there is a phase dephasing, or there is a phase delay, you can say. There is a progressive phase delay, because you have a source here, you have a drain here, you have a gate here, another gate is here, another source is here. So, when you have the gate manifold, the signal is coming and propagating, no. So, farther away from the point where you are feeding the signal in, there is always a phase delay that will happen if you are not designing properly. Because of this phase delay, that the signals are not in phase now, there is a dephasing, you can say, at the far end of the device, as the gate finger, the gate fingers, the fingers that are far away from the input gate feed in a multi-finger device will be progressively out of phase. So, because of the out of phase, there is a further degradation of the signal and a further degradation of the gain. So, it is very important to understand that a gate finger is a very critical component in a multi-finger HEMT. It can be modeled by incremental series inductance, capacitance, resistance. The fact is that there is a gradual dephasing if the gates are very wide, and secondly there is a overall attenuation of the signal as the signal is propagating along these gate peripheries. These two factors bring the gain down, and that is not a good thing. So, what are the major layouts or designs that people have used in order to mitigate these issues as far as practicable? How can we overcome these issues to a large extent such that the gain does not suffer while I have a large multi-finger array of gate widths, because I need larger gate widths to get to higher power. If I get higher power, then I can get more application in radar, satellite communication, etc., etc. For academic papers, watt per mm is okay, but for real world application you need higher power. That is why you have the multi-finger devices. So, how do they do it? They do it using different architectures. So, here we are showing the street of those different architectures. So, you can see here this is the drain. So, the drain finger is this, correct, and the gate, the black one is the gate, is coming below the, this is the source, this is the source, this is your source finger, this is your source, this is your source, this is your source, this is your source, this is drain, this is drain, this is drain, this is drain. In between there is gate. So, the gate, the black line in the gate is coming and feeding to this gate bus bar, but that gate bus bar is actually running below the source. How they are running? They are running using a concept called air bridge that I will show in the subsequent slide. So, the gate and the source fingers are not touching each other, but there is no dielectric between them also. So, they are like a bridge over the air gap. So, this hole is called a via hole. Essentially, I will come to that also. You etch the substrate thoroughly from the back side until you see the metal on the top. So, you have a metal here, this is a metal, from the back side of the substrate you etch until you exposed, you etch all the gallium arsenide and whatever until you expose the metal from the back side and then you fill it up with metal. So, this via hole connects that the top source which is grounded, this is grounded, it connects to that bottom back side which is also metallic plane, it is a low inductance in a source, it is a ground inductance plane you can say. So, the source is connected metallically to the ground plane below, it reduces the source inductance L, as opposed to getting wires done, you are directly grounding the source to the backside inductance plane. The backside also provides this ground inductance plane which is very important for RF devices, otherwise loss will be very high. So, you have multiple finger, here you have only 4 drain finger, 5 source finger, but you can have more. The more the fingers, the more will be the power, the more will be the current. So, this is called the gate side source via. The source vias are on the side of the gate. This gives you a higher packing density because it is very compact. This structure is not very packing efficient because you are extending the source on the sidewise. The source via comes on the side and instead of the gate and the source overlapping like this, here the source is overlapping. So, there is a drain here, you can see that there is a drain here, there is a gate here, the gate has no problem, but the source will go from source to source to source jumping over. So, if there is a like a drain line like that, there is a gate line like that, there is a source here like that and there is a source here like that, then the source will jump across the drain and the gate. I will come to the picture. Okay. So, the source will jump, this is called air bridge also. So, the source will jump here. This is actually good for reduced inductance because you have a via hole and you have an air bridge here. This structure has no air bridge, the source, this is your source, this is your source, all the source should be connected together to the ground, they are connected by the via, this is all via, which means there is a hole in the substrate through which the metal on the top is metallically shorting to the metal below in a plane, in a metal, nickel or copper or whatever in the metal below. So, that metallic short is creating the source in a reduced source inductance, and you do not need air bridge because all the source is grounded to the bottom. However, people also do air bridge on top of that, like the bridge will go like that. There could be via also, especially for high power devices you could have both air bridge as well as via. The via serves 2 purposes, I mean more than 2 purposes, maybe it also takes the heat away by the way. It helps short the top ground, the source ground with the bottom ground, it introduces a ground inductance plane. It ensures that all the ground is one ground, otherwise if your top is not grounded to the bottom below, no, so then your top ground and the bottom ground could be actually 2 different grounds, that is a very bad thing. So, it ensures that everything is at the same ground. And the gate to gate pitch, if I remove the annotation here, the gate to gate pitch, this gate to this gate, that is a pitch, this gate to this gate, this gate to gate, this gate to gate pitch needs to be a certain distance because around the gate drain is the hot spot, all the temperature is very high because when you operate these multi-finger devices they carry much higher power at higher frequency, so the powers go just crazy. So, your hot spots will be here. So, your gate to gate pitch cannot come very close, it could be say 40, 50 micron, maybe 30 micron, etc. You cannot bring it arbitrarily close. Okay. If you want to increase the packing density, you have to bring the gate finger closer, your hotspot will become more prominent and your device temperature will rise, which is a very bad thing because the higher device temperature reduces device lifetime and reliability. Heat sink, getting a proper thermal management on the such power amplifier wafer is very critical. We will also talk about that subsequently and towards the end of this course, but just remember that higher temperature is not an ideal thing for any device from the reliability point of view or performance point of view. So, with that we will come to the conclusion of this lecture 25, where we are just starting pseudomorphic HEMT, but we are taking a detour to understand the device layout for multi-finger HEMTs, and these concepts of multi-finger HEMT, air bridge, source via ground inductance plane etc. are universal for all kinds of FET, especially compound semiconductor FET. Gallium nitride HEMTs also will use them, pseudomorphic HEMTs use that, regular gas HEMTs, MESFETs, they all use this concept. It's just that I am discussing them in the week of pseudomorphic HEMT, okay. But these are very important to enable power amplifier that handles much higher power densities, okay, with multi-finger topologies. So from in the next 3 lectures we are going to continue on this discussion, by the way, and we will come back again to pseudomorphic HEMT, the mainstream discussion of pseudomorphic HEMT, what are their advantages, what are the challenges, then we will go to indium phosphide HEMT, then we will go to metamorphic HEMT and conclude this week, okay. So thank you for your time, I will come back and see you in the next lecture.